Okay, let me share my screen. So basically, I'm creating two notebooks. One is this age and gender, and one is this. We'll cover this. This is easier, and
Okay.
everybody can understand it. And after today, next day we'll do this.
Okay.
Basically, I'm doing this because this has both age and gender prediction. So both category as well as regression or continuous variable prediction. Like age is
Correct.
continuous and gender is male female. The way I am doing it is like this will run in your browser, and
Hmm.
even the data set will be in browser. So basically,
Hmm.
it will take your Google Drive,
Hmm.
like in data aligned. So your data will be something like this, like human images.
Hmm. Hmm.
So it will download the data set in your Google Drive,
Hmm.
and it will try to learn, like given a human face image, what is the age and all those kind of things. It's a
Hmm.
2 GB data set. So
Hmm.
I'm doing it in a Google Drive way because I don't want to depend on personal PCs because some people might not have even 2 GB.
Hmm.
So
Hmm.
this will all be done
Collab.
in cloud, yeah, in collab and cloud. Basically, it will
Yeah.
use your personal drive to save the model as well as data.
Hmm. Hmm.
So this is one problem. Another problem is we will cover today is so this is age and gender. It has both flavors. You can predict the gender as well as age.
Hmm.
Today I will be covering this problem, which is much easier problem and easier to understand and go through code. And basically, this is much easier. And this is just a category prediction. Basically, you will be given handwritten digits
Hmm.
like
Hmm.
these, and you try to predict what is the digit, like what is the digit, what the, so basically you want to learn a model which will say, is it a 3, is it a 2, is it a 2, is it a 0, is it a 6, or something like that.
Hmm.
So this data set name is MNIST. This was firstly used in 90s for pin code detection as well as check. Like people used to write amount in checks like $1, $2, $3 or something like that.
Hmm.
So this is generally used in that processes.
Hmm.
And the good thing is why I'm doing this today is it's very easy to train this model. Like it will take at most 2-3 minutes to train this model to
Hmm.
very high accuracy, actually, like 98%, as like near 99% accuracy. And people can actually then see their predictions also. So it's very
Hmm.
easy exercise. So let's do that today. And
Okay.
next day we can do something more complex, like actually
Age and gender.
predicting, like given this image, predict what is the age. Like you cannot predict the actual age because you know, like it's very hard to predict in age just from like it will do something like it will predict some age, and then you can do something like this might be 15 to 20 years old and the gender is female. Like you can then classify like what do you want to do, like a mapping.
Okay.
So let's go through this easier example today. So
Mm-hmm.
this is I'll share the collab with you, so anybody can just copy this and just they just have to click the play button.
Yeah.
uh, Even if they don't follow the video, they don't want to follow the video, they can just go through this text, and it's very like self-explanatory text, and
Hmm.
pretty much has everything, even if they don't want to go through the video. Some people just want to go through the text because it's very
Correct.
fast, so that is good for them. So basically today we'll be covering basics of PyTorch with the example on OCR. Like
Hmm.
given a text, can you classify which digit is it? Like out of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, there are 10 classes. You want to predict which class is it. So this is a
Hmm.
supervised training problem,
Hmm.
and it is a supervised training problem. Also, this is a category prediction problem, like
Hmm.
predict the category. Okay, so we'll see like what are the things, like very, very basic things which are needed. So first thing is you need some libraries. You don't
Hmm.
need to worry about everything. The most important library is Torch, which is
Hmm.
PyTorch.
Hmm.
Okay. In this collab, this is pre-installed. Most of the collabs now have everything pre-installed.
Hmm.
So just click here and this will import your PyTorch library.
Hmm.
Uh, okay, it's little bit slow, but yeah. Let it do the work.
I think it is
Maybe.
warming up. No,
Yeah.
collab have to initialize it. Has to be
Yeah.
initialized, right? I think it is just warming up.
So it's just good now. It's working.
Yeah.
Okay. So this is gone through. Now I'll tell you what are the basic things. Like this torch is PyTorch library and is neural network. So basically what we are covering now is more hotshot kind of thing. We are covering neural networks or deep learning kind of networks. Basically, we'll be covering convolution neural networks, deep learning, and neural networks. These are mostly buzzwords. There isn't any big thing here. If you just follow this, you will be able to do it. But after that, you can go through if you want. Like this is more like a breadth first search kind of a tutorial, not a depth search tutorial.
Hmm.
It will go through a bunch of things which you can just combine together and make a model and just train it and then get the results. But if you want to go too deep, I can also give them some links to follow, or we can cover in other tutorials also. So NN is a neural network. This is nothing, just a function. Torch vision is most like PyTorch also provides you matplotlib kind of a library where you can visualize stuff. That's it, nothing else. And PyTorch transforms. So I'll tell you why the transforms are needed. Transforms are needed because what happens is when you are training, you are sending a network some image. Okay. So what you do is you also sometimes shake it. You sometimes rotate it. So you make the problem a little bit harder. So let's say you are teaching a very small kid. You will not give the exact apple image. You will try to rotate the apple, make it vertical or something like that. So basically you will try to shake the apple so that person will recognize this is apple from different angles also. So this transforms will basically just shift the image around to make it harder for the network to learn. So the thing is, the more harder you make it at the training time, better it will be at the testing time. So if at the training time the problem is very easy and somehow the problem becomes harder at the testing time, then the network will not know what to do. So it's more like how you teach the student, like our class teachers. They will give us basic problems and then they will also give us harder problems in the classroom. And at the test, it will be a mix of both worlds. Okay. So this is a transform. You don't need to concentrate much, just like basic things which are happening. It's like printing, which version of this have. So the good thing is the PyTorch, it has everything. You don't need to implement anything actually. It has the data set itself. Like I would say like this is the major chunk of machine learning which is happening in industry, getting the data. But for MNIST data set, because it is very standard data set, this is already done. So all the data engineering and all the thing is happening in this, like I would say 10 lines of code. But in real life, this is the major chunk of ML engineering work, getting the data, finding the data, getting the data, making it cleaner, loading the data. This is what is the major job of like when I was working as an ML engineer. But here it's done for you. Like it's just 10 lines because MNIST data set is very classical data. It's very small data. So it's done for you here. Okay. So we'll go through the each line, what is happening. So here we are getting some transformations. It's nothing. Basically, we are not doing any transformation now because it's a very easy problem. We don't need any transformation. But in the real life, you will need rotation. You will need translation, like a random rotation, adding some noise. So those kind of transformations you will need in real life. For this MNIST, we don't need. Okay. Now what is batch size? I will tell you what is batch size. Let's go through first this code. So basically, it is basically from Torch Vision. So Torch Vision also has data sets, and it is getting MNIST. Okay, and it's saying download to download it, and basically the train is true, then it will only get the training data set. So basically, when you get the data set, you need to divide it. Generally, people divide it into 70-30 or 70-20-10. So what is this division? Why is it this division has to be random? What you do is you get the data set, divide it randomly into two ratios. For first part, we will divide it into two parts, 70 and 30. So what is 70? 70 is the major chunk of your data set, which is known as the training data set. So this is the training data set, for each image you have some level, and this is what you're gonna use your model to train on. Other
So
70.
this is part of your developing the model. So 70-30, you will develop the model with 70% data, and you will
Yeah,
use the other 30% data to test. And then
yeah.
when you deploy it, you will actually run it on the
See,
actual data.
actual data. So some people, what they do is they also do 70, 20, 10. So on 70 they train, on 20 they use it as a local validation, and 10 they reserve it for the end scenario.
Okay.
Like at the end they will have a golden data set, and then only then they will touch that. They will never touch it. First
Okay.
on 20 they will prove that, hey, I'm working, and then they will only touch 10 when at the end of the moment. You cannot touch 10 ever. You can only touch only once. So because we don't want any bias coming into your networks. Okay.
Okay.
So basically you have the training data set. This is just getting the paths. Once you have the paths, you get into the data loader. This is basically a iterator, which we normally have in Python. Iterator, basically what it does is, whenever you call this train loader, it will give you 32 images, like a batch size, based on batch size. And this is what it is. You call it, it will give you 32 images randomly out of the 70. This is what it is doing. It will keep doing that, doing that, doing that. How much time do you want? Okay. Similarly, we are also loading the test data set here. Okay. Just by doing train falls. Okay. This is just code. There isn't anything like amazing or rocket science. Now we have batch size 32. So what it will do is, let's say we are training something. One thing you can do is you can get one image, send this to network, and train the network using one image, and then get the next image, do that, next image, do that, next image, do that, next image, do that. But now, since we have GPUs, which are like better than CPUs in going through parallel data. In CPUs, you want some like sequential data. In GPUs, you have a parallel processing. So what we do is, to do it faster, we'll give the 32 images parallelly. Okay, train it on 32 images, and then whatever the results are coming, we'll say like whatever is right, good, whatever the bad, we will punish the model and send the next batch of 32. So more like a batching is happening, so making the process faster. There are other use cases of batch size also, but now we can just say like, okay, as we have more space, we can actually train it parallel. I will ask people, I have also written in this line, like you can like increase or decrease this batch size. It doesn't make any difference. It will have a very minute difference in the final accuracy. Generally, bigger the batch size, better the model. Why is that? We can discuss it later. But generally, if any pipeline, we try to push the limits, and how much the RAM does the GPU have, we push it to limits. Let's say it can have 64 images, then we'll push that limit to 64. So this batch size actually depends on the machine you are training.
Got it.
So if your machine is very big, you should make it 128 or 200. Google generally also trains on tens of thousands of batch size. Okay. So bigger the batch size, faster the training, better the experiment. Okay. So this is what is happening here.
Okay.
Okay. Now comes the code where we are gonna basically, this is now loading the data. It's very fast actually. Now as now we have this train loader. Okay. From train loader, we just created a very small function, imshow, which is just gonna show you the image, whatever the data you have. You use the iterator on the train loader, and it will give you data. And basically, in Torch Vision, we have things like make grid and everything provided. You just get the images and show it. So this is 32 images, like 8 cross 4. So this is the training data set you are getting, 32284068796. So it's gonna be random every time you do it, because it's iterative function. So it randomly picks up something. Okay. So this is the input images. As you can see, they are very complex also. Like it's very hard actually. Like what is this? Like this could be 6 also, but this is 0. Okay. What is this? I actually don't know what is this. It could be 7 or 4 or something like that. So data is very hard actually, if you see. Okay. So for these for these images, we also have labels. Like you can just do it, do the code plus, and you can see the labels. Okay.
Hmm.
So this is 9, 1, 0, 4, 7, 7. This is 7 actually.
Hmm.
Okay. So this is the labels and this is the images. Okay.
Hmm.
So basically we are going to send the images to the model, and now we know the labels. Model is going to do something over it. And if
Hmm.
it does correctly, it is like, let's say it's saying like, okay, this is 9. We are going to say very good job. And if it's not good, then we are going to punish the model. Basically we are going to use the minimizing the cost function that we discussed yesterday.
Hmm.
The cost function is 0. The loss is 0 if everything is right. The loss increases as you are getting something wrong. We
Hmm.
want to decrease the loss. So
Hmm.
basically we are going to follow the same approach that we discussed yesterday, that finding the minima of the loss function. Okay.
Hmm. So
Now,
the
yeah,
code which you have shown is primarily to preview the data which
yeah,
is there,
this,
which we are going to
this,
train
yeah.
and test.
So this job, the thing that we did right now, it is very important for anybody. Everybody should do that. Like I would say, like in ML, like the ML engineering role, your 60% time is spent on data pipeline and data issues, like
Hmm.
getting the data correctly, and 30% time is spent on actually exploring the data. If you are not
Okay.
exploring the data, let's say this is now 8, in like this thing is 8, but here it's 9, then there is something wrong in your data pipeline or the way you are getting iterations. So you
Hmm.
have to get it correct, because if these labels are wrong, so basically in machine learning we say garbage in, garbage out.
Hmm.
If your data input images and labels are garbage, they are not matching, then the model is going to do random thing. It's going to
Hmm.
train, but it's going to do something random. It's more like you're teaching a student the wrong thing. So then
Hmm.
in the exam, whatever the student going to, you never know.
So in this
So this
case,
is, yeah,
the image and the label are
should match.
together. No.
Yeah,
So someone have actually labeled the images
yeah,
probably
yeah.
manually or
So
probably
yeah,
using some
manually.
automation.
No, you have to do it manually. That's why we call it ground truth also. This
Okay.
label is ground truth. Like this is the ultimate truth.
Hmm.
Image is the input data, label is the ground truth. This is the ultimate truth. If this is wrong, your model is gonna be wrong. So
Okay. Got it.
label has to be like in my last company, 5 humans will go through the same label to actually check if the label is correct or not. Because if there is an error in label, you are not gonna learn anything.
Got it.
Okay.
Got
So that's why we say like this exploring the data is the most important part.
it.
To
Got it.
get better at it, people should use Matplotlib or even Torch Vision provides some libraries. So you should get better at it. Like we should be very good at it, like visualizing the data.
Got it.
People should spend 30% of the time at visualizing the data, 50% of time getting the data, because like getting the data is very hard. The systems are very complex.
Hmm.
Getting the data is very hard part also.
Got it.
Now, as you have done the exploration, like your labels are looking good. Actually, we should actually check right now. 9, 1, 0, 4, 7, 7, 2, 2, 2, 6, 8, 3, 8,
Got
7,
it.
0, 9. Yeah. So as we know, like looking at these labels, it's looking nice, but we should spend way more time on that. Randomly do it again and again and again so that it is correct. Let's do it once more. This part is very important. If somebody misses this part, then they are gonna have bad results. Like
Yeah.
like looking at this, still I think this is good. Okay.
Yeah, not only
Now,
here, even in
yeah.
regular IT also, a lot of people doesn't spend
Mhm.
time understanding the data and they go ahead and build the applications. And then
Yeah,
they
yeah,
will be running into a lot of bugs. And even
yeah.
while learning also, I'm seeing that a lot of people doesn't observe and understand what is going on. After
Hmm.
executing,
Hmm.
they will only focus on whether it is executing or not. They are not
Hmm.
doing
Hmm.
that
Hmm. Hmm.
extra validation whether it is yielding the correct results or not, because
Yeah,
it takes some overhead, and most of the
yeah,
guys want the instant results, and people don't understand the value of this, which will
yeah,
eventually improve their
yeah,
productivity. Yeah.
yeah, yeah. So for example, this thing, if I ask you without looking at label, what is that?
Hmm.
So, humans, I think what they have marked is this is 8. So
Hmm.
if this comes in your test case, something like that, that will be output as 8. You
Hmm.
shouldn't be surprised by then, because your input data and input labels and ground truth think this is 8. So if
Hmm.
something like this is coming output, then if your manager is asking, hey, this looks like a 1 to me or something else, then you should complain that data set was saying this is 8. So this is what model gonna do. So
Correct.
model doesn't have any intelligence coming from any other third party. There isn't anything like that. It's just whatever you're giving it, it's just gonna learn that. It's very easy.
Yeah. Yeah.
It's more like treating it as a child is the best analogy, I would say.
Yeah.
Okay. So here we are, like you had like a batch size of 32. Basically here we are seeing like what is their shape and all.
Hmm.
You need to check that what is the shape. So what is the shape of this image now? So as you know that there are 32 labels. If you can see here, these are 32 labels. Okay,
Hmm.
which is correct. About what about the input image? Input image. So we know like the batch size is 32.
Hmm.
As this is a grayscale image, this image is a grayscale image, so this will only have one dimensional, one.
Hmm.
If there is a colored image, this will be 3, then
Hmm.
RGB.
Hmm.
Okay, and this is 28 by 28 image, so 28 pixels this side and 28 pixels this side.
Hmm.
Okay, so this is a grid. Basically, if you look at one single thing, this is a 28 by 28 grid, and it have a 0 to 255 value at each cell. This is how
Hmm.
you make a image. Like even in your TV screen, it has pixels at each grid. So this
So
could be yeah.
in this case, you are actually getting the metadata for the image. Uh,
So this is the shape of the image. Yeah,
yeah, that's what it's all metadata, label,
this is
shape,
all
everything.
metadata. Yeah,
Yeah.
yeah, yeah, yeah. So basically checking like what are we doing basically. That's what we are doing. Okay.
Got
Now
it.
comes the modeling part. So if somebody is eyeing for a ML engineer role, this part only will take 5% of your time. Like in
Hmm.
my last companies, I never actually made this. Like in
Hmm.
2 years, I never made any model. Why? Because most of the models are already implemented for you. You just have to make a data pipeline, explore the data, whether this is correct or not, take the model which is available on the shelf, use it, because modeling is, I would not say hard, but modeling is experiment intensive. Like you
Hmm.
never know which model is best. Nobody knows. There isn't any science. This is more like a art. So whatever the model is given, most of the people use resonets nowadays. Just use the resonate and go with it. Just bring the experiment. Then later on you can go back to the model. Wanna change something, you can change small things, and then maybe observe a improvement or maybe not improvement. And then based on that, like it depends like how much bandwidth do you have or machines
Hmm.
you have.
Hmm.
Just choose a single model, done with it. If you have really good data, clean data, and make sure that data pipeline is clean, every model will give you very good results. And at the end, the difference between best model and the worst model is going to be only 0.1% or 0.5%, something like that. So that actually is more like if you're doing something like a PhD, that is useful then. But if you are
Hmm.
in a production kind of environment, this point one, point two, nobody cares. People just want 95 or above, something like that. People don't care if it's 95.1, and if you take like 1 week more to deliver that. They don't want something like that. They want like 95. That's it. That's good enough for us. Something like that. Okay. So modeling, you should only give 10% of your time or 5% of your time, I would say. So now we'll go into the model, what is happening. So as
Hmm.
you remember in from PyTorch, basically the base class is still neural network. This is a neural network. Okay.
Hmm. Hmm.
Now here, if you remember from the last class, here are the weights. The W that you remember, we are initializing those weights. So this is
Hmm.
gonna initialize those weights random. Like firstly, we'll randomly initialize them, and after initializing them random, we are gonna change them slowly based on how your cost function is decreasing. We are gonna select the W's which have the minimal cost function. Okay,
Hmm.
so that part is clear. So I would say for now, what the convolution, I'll give you a brief what is convolution neural network actually here. Okay, so
Hmm.
what is con 2D doing? Con 2D is inspired from I. So let's say I give you some image of let's say there is a big painting in front of you. How do you
Hmm.
analyze it? So what you do is you start analyzing from the top, and you go row by row, row by row, row by row, row by row, and you get the full image now. Now, once you have full image, then you decide what it is. Like, is it an apple? So you do this very quickly. That's why you never analyze it. But your eye has a very small receptive field. Like the actual focus that you can make, it's very small patch. So what you do is you analyze this. Like some people, if you have seen, like they will move their eye very quickly to see what is happening in front of them. So what they are doing is they are analyzing what is happening. So this is known as convolutional neural network. Okay. The convolutional neural network, good thing is it sounds very complex, but internally it's very easy. And the good thing is it's already implemented for you. Like just do nn.con 2D, voila, you are done. You don't need to do anything. You don't need to implement it. Okay. I'll go through what this is doing. What are the variables? So this is saying in channel. Okay. So your input image depth is 1 because it's a grayscale image. Okay. What this is doing, this is kernel. So what is this is doing is like giving more capacity to convolution. If people want to experiment, they can just increase this kernel size to 4 or 5 or 6 or whatever they want. Okay, you can have 100, 200. It depends on the capacity of your network. So currently we are giving 10. You can also give it 3 or 10, whatever you want. Okay.
When you say
But
capacity of network, is it network or
capacity of convolution layer. So basically, now what is happening is you are training on weights. Basically, how many weights you want to train. This is what this is doing. This is going to multiply the number of weights. So the bigger the number is, the more weights you are training. So the better your network becomes. So this is what is happening right now. I will tell you like what is should be the limit, but generally whatever it is, just keep it that. You can make small changes in it, but it doesn't matter a lot. Okay. But for starters, I think the people should not concentrate much on like small details, because nobody knows why the 3 should be good. It could be 7, it could be anything, doesn't matter. Okay. Because it's not still not perfect science. It's more like we say like it is giving it more capacity to learn more complex things. But if your input is not that complex, even the smaller kernel size is okay. Okay. So this is like more like a capacity. You can say kernel is more like a capacity. Okay. So what it is doing is it is saying the input to me will be 1. So this is what you have to change. If the input image is RGB, you have to change it to 3. Otherwise it's 1. Out channels, you can do whatever you want. Some people do 32, some people do 64, some people do 4, whatever you want to do. Just do. This is also a capacity. So these two variables are more like capacity. If you don't understand anything, just understand these are capacity. And we can go into these details later on also. Okay.
Okay.
So now this is only one convolution layer, and then there is some linear layer, and then so basically this is like layers. This is why it is known as deep learning. This is like layer 1, this is layer 2, this is layer 3. Okay. So our brain, it has multi-layer structure. One layer, first layer is here, the image goes into retina, then second layer, then third layer, and at the top we take some decisions back here. Okay. So similarly we have different kind of layers. So like convolution layers, there is a linear layer also. Convolution layer is more specific to image. Linear layer is very general layer, like a linear layer. Okay. So what is happening? You should observe what is happening here. This is what you will need to change. Okay. So what is happening here is, so another thing you need to notice is it's saying like, okay, I'll go from this dimension to 128 dimension. Next layer input should be 128, and I am going to 10 dimension. Why 10 dimension? Because you have 10 categories of output. So basically it will have 10 variable, 10 outputs, and output number 0 will represent how sure whether the output is 0. Output number 1 will give you how sure I am that the output is 1. So basically 10, you can assume like it's a 10 variable output, and you are going to check each output. Is it 0? Is it 1? Is it 2? Is it 3? Is it 4? Something like that. So the output is 10 now. Okay, because you have 10 categories.
Got it.
The only thing you need to remember is whatever the output of this layer. So this is saying like, from this thing I'm gonna do this. So whatever the output of this is coming to this D2 layer, so the input should be same. Then the only thing which we'll need to change, or the people who are practicing ML will change, is only this variable. If your problem has only 5 categories, they will do something like that. If the problem has 2 categories, they will do something like that. That's the only thing which people change. Like This is what I have done for 2 years, just changing this variable. Like how many class do you want to train on? Okay, 5. This is 5. You want to train on 10? Okay, 10.
Okay,
Okay.
so
So this, yeah,
in case of gender prediction, it is
it
only
will
two.
be 2. It will only be 2. The same model. You see, feel the flexibility of this model. Like we are going from OCR to gender, but the model remains same. Only the output changes, but it will be still be good. This is the beauty of deep learning. You don't need to know a lot about model. Just changing the output dimension will give you a very good model.
Got
Okay.
it.
This is the beauty of deep learning. That's why everybody now says I am a ML engineer, because you don't need to do anything to be a ML engineer. You just need to change the output dimension, and this now you are a ML engineer. Okay. So now if we go to this, so basically what this is doing is this is the initialization of weights. This is saying like, okay, I'll have these weights. How these weights are connected, this is how you are saying. Okay. You're saying it, this is known as a forward function, like how it is progressing. So the X is the image. Image will be coming in. I'll be passing through the convolution network, and the output will be X. Then this will be passing through ReLU layer. This is also a layer which is a non-linear layer. You don't need to know much, but this is some kind of layer. We need to do that after every layer. Okay. Assume that image X is coming, output is X, then X goes through ReLU layer, output is X. Now you flatten it. You can just ignore this for now. Okay. Now this thing goes through the D1 layer, output is X. Now this goes through ReLU. We have to do this every time because this is a neural network. You don't need to know much about it, but I'll teach you in the next lecture what these things are. Okay. As we go deep into neural networks. But on the highlight, if you want to remember anything, the image will go to convolution layer, then D1 layer, and then D2 layer. So this is what is happening. Image X coming to convolution layer, getting out, and then going to D1 layer, getting out, and then going to D2 layer. Okay. After D2 layer, this is the output you are getting. And this is the output, which is a 10-dimensional output. You're going to say what is the class that you're getting. Okay. Now you have a model. You are calling it my model, or you can call it whatever you want. Okay. Okay. Now you have the model. This is a model class. So you initialize a object of the model. Now this is your new model. Okay. Now what they're doing is, this is also an important part to just check whether everything is fine or not, because maybe you miss this. Let's say now we have output the 2. Let's say I run this. Now it will be wrong.
Correct. It has to be 10. Yeah.
So this is 2 now. If you can see here, the output size is 2. I actually want 10 because this is not gender classification. The data set is OCR classification. Now I'll reboot it, and the output should be 10. So this is also a very important step to see what is the input dimension of your model and what is the output dimension of your model. Okay, as the images are going in. So this is, we call it like flushing the pipes. Just seeing like how the output is going to come. We know like our model is very bad because it's a random. It will do random things. Okay. Now comes the part which is the 5% of your ML engineering. Like I would say like getting the data was 50%, exploring the data was 30%, making the model was 10%, or I would say 5%. So this is the 10% part, which is training the model. Okay. So how do we train the model? Basically now, if you remember, now we have initialized the weights. Most probably they are random weights. They don't have anything. Okay. So here only 2 things which you need to remember from this lesson. One is learning rate. We generally make it 0.001. Now you can ask, why is that? Because it works. That's it. There isn't any science behind it. Why it works, why doesn't it? But generally, learning rate should be 10 raised to the minus 3 or 10 raised to the minus 2 or 10 raised to the minus 4. You can basically try each learning rate. I would suggest people, when they're trying this experiment, change the learning rate to whatever you want. And what is number of epochs? Number of epochs is how many times your model is going through the data set. Let's say now you have 64 images. Okay. Your data set only has 64. In this case, we have 10,000, but let's assume you have only 64 images. So the batch size is 32. Okay. Batch size is 32. So only 2 batches will full the data. Okay. You demand one batch, you get the 32 image, you train the model on this 32 image. Next batch, more 32 images. Your model is trained on all the images. So 64 images, it is trained. But similar like the way you teach the human, let's say you're teaching a small kid, what you do is you send the same image again and again. You will show them again and again. Okay, what is this? Okay, what is this? Okay, what is it? So the number of epochs is saying how many times it has to go through the whole data set.
Got it.
Okay, generally this is 500 or something like that, 500 or 5 million or something like that. In my last job we used to do something like this, but in this small experiment we will only do this. So the bigger this number, better it is, because you are basically, what you are saying is, what is this, what is doing again and again and again and again, same image going through the data set again and again. So each epoch, one epoch will go through the data set once, two epoch will go through the data set twice. So this is what you are doing. Okay, so now we know, like I would suggest people to actually try these two things, whatever best works for them. How do you know what is the best? At the end you will get some accuracy on your test data set. You can compare those and then say whichever is the best and claim that, hey manager, I tried these learning rates, I tried these number of epochs, and this is the depth of my model with this kernel size of 5 or 10, whatever they want to try, let them try, and then show a nice graph where you have different uh, experiments that you did and different accuracies that you got, and then you can compare whichever is the best. Then you can claim, hey manager, this is what we are gonna produce. So this is how you do. But generally people don't try many models, at most one or two models, because the training time in production, it used to take us like 21 days to train single model. So if you train on, you can train parallelly, like on one machine, one model is training with, let's say, learning rate 0.1. Another machine, another model is training with 0.001. So you can have that, but the cost actually rises up as the number of experiments rises up. So generally, people tend to train only one or two models, and they are happy with that and compare 2, 3 models and say whatever is best for them. Okay. Because the thing is, you won't see big change. It will be like 95.7 and another will be 95.9. So the manager will be like, the cost is very high as the experiments are increasing. So we'll just do 1 or 2 experiments and we'll done with it. Okay, so what is happening? So you can ignore this part now. So what is this doing is, if you are training on your local laptop, then you will be using CPU. Basically, what you're telling the network is, am I gonna use CPU or I'm gonna use GPU? If you see CUDA, that is GPU. But as we are using Google Colab, so we are gonna use CUDA, which is provided by Google for free for us. Okay. So basically, you are saying like which kind of device I'm gonna use. Okay. So this function is actually checking whether your Torch or the PyTorch has CUDA enabled or not, or GPU enabled or not. Okay. So the 0, because some machines have multiple GPUs. So you can say actually tell to train on GPU 1, GPU 2, GPU 3, whatever. Nobody cares. Now here you have model initialized, then you are getting the model on device. Basically you are saying like, okay, get this model is still in CPU. Then you are saying build this model on the GPU, because on GPU training is much faster. Okay. Now this is the cost function that I was telling you yesterday. We will go into details tomorrow, but if somebody just want to do like a training for category, the cost function is gonna be always same, cross entropy. What this is doing internally is, basically it's saying that whatever the category that is expected, do that. What is your output gonna be? Your output is gonna be, it's gonna be one hot vector. Now this is another buzzword. So what is the actual thing is, so now you have 10 categories. Okay. For each category, it's gonna give you some output, which is more like a probability that this is this. Another thing to make clear here in ML is, everything is probabilistic. And I'm saying probabilistic doesn't mean you have to do Bayesian and learn probability. You only need to have a probabilistic mindset, because a lot of times your output is going to be wrong. That's why ML is not still widely applicable to medical field or self-driving. That's why we don't see self-driving cars, because it's probabilistic. because sometimes it will give you good results, sometimes it can also give you bad results, as you might have seen in Google Translate also, and the other apps that people generally use. It's not always correct. Even in the
Correct.
Zoom video, it's not always correct. Sometimes your chair is considered as human as well.
Yeah.
So this is you need to have a probabilistic mindset. If some managers are having very rigid mindset of a software engineering, that if 1 is equal to 1, then print this, if 1 is equal to 2, then don't print this. This is now how the things work here. You have to make a probabilistic mindset that it might work sometimes, it might not work sometimes. So but you can get some numbers like 95% accuracy. That means 95% of the times it will work if your test data set is similar to training data set. If there is some case which your training data set has never seen, your model can do anything. That's why that Tesla accident occurred, where there was a truck in front, like a white truck, and the sunlight was coming. So training data set had never seen that kind of case. So the car assumed this is open sky. It moved into it, the person died. So you have to have a probabilistic mindset. This is not like if else. This is like learning something new. Okay. And it's not that smart actually. That's why you have need to concentrate a lot on your data pipeline. Your data must be pure, it should be good, and you should need to have a lots of data. Only then you can make sure that whatever the production you are shipping, it's gonna be good. Okay. Like in my last company, we used to have like terabytes of data. So this is just saying like what is the cost function. In category problem, we are gonna have gross entropy. In regression problem, which is more linear problem, we are going to have MSE, mean squared error. So just need to do remember two things. Whatever the problem you are doing, if it is a category, gross entropy. If it's not category, MSE. It's already implemented for you. You don't need to implement it. If you don't know what is doing internally, you don't care. Just put it. It will do it. Okay. Another thing, what actually it is doing is, so now you have 10 categories. So each category is giving you some probability. Like it thinks that it is 0 with probability 0.1. It thinks like, so let's take a very small example. So for this case, let's say this. So when you input this small 6 patch image, this 28 by 28 image, the model is going to output. What does it think it is 0? What is the probability? It's going to say 0.1% probability that it could be 0. Then what is the probability that it is 1? What is the probability that is 2? What is the probability that is 6? So the probability that it is 6 should be higher than others. So that's how you select. You basically take whatever the highest, what, like if you ask me, let's take a very small experiment. You are asking a very small kid, what is the probability that this is 0? He's going to say maybe 0.01. What is the probability that is 1? He's going to say this does looks like 1 actually. So 0.2. Then what is the probability this is 2? Doesn't look like 2. 0.1. So this is how it works. And when you tell him, does it look like 6? What is the probability that does look like 6? He's going to say, yeah, 0.99 or maybe 0.1. It does look like 6. So you are going to take the highest answer given by him, and this is going to be your output. Okay. So what is cross entropy is doing? It wants everything else to be 0, like probability of 0, 0, probability of 1, 0. It's going to punish it. If it's going to increase than 0, it's going to punish it. And it wants probability of 6 to be 1. So this is what the cross entropy loss is doing. Basically punishing it when it's wrong and giving it better when it is right. Okay.
And this whole process will be done by comparing with label, right? So because you will be having label, so it will compare with the label.
Yeah. I'll show you where it is happening. Okay. So now this is the optimizer. So what the optimizer is, people don't need to actually know what the optimizer is. Basically, this is the teacher. Now you know the cost function, but somebody has to use that cost function and then make it work. So you can assume optimizer is just a teacher. Whenever you are wrong, this cost function is giving you, I am wrong. Okay. I am wrong with 0.7 error, or I am wrong with 0.8 error. This optimizer is actually showing you the direction in which to move so that you can reduce this error. So this is like a teacher which is moving with you. That's why it has the learning rate. So where does the learning rate do? Learning rate, what it does do is basically it's the speed with which you should move into the direction where the loss is decreasing. Okay. So let's say you are in some valley and you know your loss is 0.9. The optimizer will tell you, okay, I know the direction where your loss will decrease. So the learning rate will say like how much fast you should move into that direction. So if you want to train your model very quickly, increase the learning rate. If you want to have a slow learning rate, so basically it's more like a learning rate with how fast you want to learn the problem. The problem is if you have very high learning rate, then you might not even learn it because there is a capacity of a network with which it can learn. So just giving it 0.001 is fine, always, all the time. Okay. So let's say, let's do this. It's still not training the model. The training of the model comes later. This is just setting up the setup. Okay. This is for accuracy. This is just a code to actually compare accuracy. Okay. Now this is the training. Now comes the time for training. So what is happening is this, see this? This is the epoch. Like how many times, this is just a for loop. There isn't any rocket science. This is just a for loop. How many times you want to go through the training data set again and again. Okay. And what this is doing is you got the train model in the training mode here. And basically what you do is you get the loader, train loader. You go through the train loader for loop. Okay. And you get the images here. Now you have the images here. You send those images through the model. Okay. So you need to consider now a lot. So what is happening here? It's very important to know what is happening. What is happening is you have a train loader, which is iterator. You are getting some images out of it. Okay. Labels and images. As you can see, this is a training data set. Okay. You send those images through the model. The model will give you 10 outputs. Okay. Which is logits. This is, I would say this is prediction. Let me write it here. This is prediction. You're asking model why, what should be the output with these set of images. Okay. You take this prediction and compare it with labels. This is the comparison step which your teacher is doing based on criterion. Criterion is what? Loss function. You're finding what is the loss now. If the loss is very low, your optimizer will say like you are good to go. You don't need to worry. Okay. If your loss is high, your optimizer actually takes into account that loss and it will step. This is what we say like moving into the valley. What your optimizer is doing, it's internally controlling all the weights of your model and it is telling them move into the direction where the loss is decreasing. So on a high level, if you just want to understand what is happening is you're sending some images through your model, getting the loss, using the optimizer to traverse in a direction which will minimize your loss. This is it. This is what this is doing. That's it. For each epoch, like how many times you wanna go through this loop. For each epoch, you get a batch, send through the model, get the output, compare it with the ground truth. So here is the comparison happening with the ground truth. Ground truth which is marked by humans. Okay. The prediction is being compared with ground truth, which is marked by humans, and whatever the loss you are getting, you are trying to decrease that loss. And this is what the optimizer is doing. Okay. At the end, you do model.eval to see is your model, I mean, better accuracy or low accuracy or whatever it is. Okay. Now what we'll do is we'll just push this button and see how it trains. Only for 5 epochs.
Okay. And from where this train loader and criteria values are train loader value and criteria is imported?
From PyTorch. I will show you where the train loader is coming. So let's wait for this training. Usually in production, this step is gonna take for you like 7 days or 5 days. Okay, because training is generally very like you have a lot of data. So now epoch 0 is finished. The loss which is coming is 1.5956. Okay. Now the optimizer should move the model in a direction which actually reduces its loss. Okay, see, it's slowly reducing the loss. And as the loss is decreasing, your accuracy is actually increasing. You see that? But the thing is, you shouldn't worry if the loss is increasing. Sometimes the optimizer is confused, it might increase and then decrease. So this is not perfect valley most of the time. This is more like a mountain. Sometimes go up, go down, but at the end it should, like on the whole picture, it should reduce. So it's still trying very hard and getting train accuracy of 98.16. So let's see how well it goes.
And will there be a point? So for now, epoch is 5, right? So it will iterate through
Yeah.
5 times. So if we increase it to 10 or 20, will it follow the law of diminishing returns, where after certain number of epochs,
As you
the
can see, like the
accuracy?
first epoch gave you like a very high bump, and then the bump is very slow.
Yeah.
So
Yeah.
now, as you can see, 98.90. But if I run it again, you will see the something difference. Let's let's run it for 6 epochs or even 5 epochs. You will see something else. Like 98.9. Now you will see difference because this is probabilistic. Like there is
Got
some
it.
probability because optimizer is trying to move into some direction, and then weights are initialized randomly. So the starting point is always different. So this is very probabilistic model. So what is this train loader? That was your question. So this is basically data set. This is the train loader.
Okay. Got it.
Yeah, you made it. Yeah. So that's what I'm saying. Like this is the 50% of your work.
And what about criteria?
Criteria is this, just a single line. This.
No, but from where you have imported it? Okay, got
this
it.
is
Okay.
this is from
Cross entropy.
Pytorch. Yeah,
Criteria is the object of type cross entropy loss. Okay.
Yeah, because this is a category loss, so cross entropy. If it was like a regression, then or the linear regression, you will do MSE. Instead of this, you will write something like MSE. That's it.
Got it.
The thing is, it's very easy. Like you should just decide, like, okay, this is what I will learn initially, and just try it. That's
okay.
I think that's the good way. See now, even in the 0 epoch, it went to 99. So this is completely random, but it should go to the similar level at the end.
Okay. So
Okay.
Does it remember the last one? Because
no. Basically, what you have to do is you have to save this model in a pickle file or something like PTH file. Okay. You have to save the model, otherwise, after the session is gone, this is deleted. So now, as we see, like train accuracy is pretty high. Okay. Now we have to see how is the test accuracy. This is the training accuracy. This is actually evaluating on the same data set on which it was trained. This is 70% of the data. What I am telling you is basically this is more like a exam before exam. This is more like a revision test. Like, okay, I have taught you this. I'll ask the questions from this. But now this is the test accuracy. So the get accuracy method, this is very easy methods. Okay. Just comparing whether you are good or not. That's it. If the prediction is good, I'm going to say 1. If the prediction is bad, I'm going to say 0. So I'm going to see like how does it behave on that data set which it has never seen. Okay. Now this should be lesser than train accuracy because this is harder. As you can see, 98.4. So if your manager is deciding on train accuracy, that model is good, this is wrong. You should always test on test accuracy because this is the data set which it has never seen. If it will give you some data set it has never seen, this is what is going to happen in real world. That you are going to get some data set. How are we doing this? Basically, in the model, you're sending in images, getting the outputs. That's it, and comparing it with labels. Okay. Now we'll see like what is actually happening. So this is your images. You have a batch of 16, depth of 1, 28 by 28 images. This is just visualizing those like 8 to just 16 images. Okay. Let's see what are the images. It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 1, 2, 3, 4, 5. Very symmetrical actually. Okay. So now let's see if we send these images, which you are just seeing now through the model. This is your model. When they say like, what is the machine learning model? This is just an object with some weights. Okay.
Correct. Yeah.
I'm using it. Now we got some outputs. Now let's see the output shape. It should be 16 by 10 because there are 16 images. For each images, there are going to be 10 outputs. Basically, for each category, what does it think? Now let's see the first output. Output 0. This is output 0. As you can see, probability that this is 0, this is very, very low, 0.000000003. Okay. 10 raised to power minus 19. Probability that this is 1, it's perfectly 1. Probability that this is 2, very low. Probability that this is 3, very low. I would say like for this 0, 1, 2, 3, 4, 5, 6, 7. As you can see, for 7, it's little bit higher. It's very, very, very low, but higher than others. Can you guess why?
Because 1 and 7, there are similarities compared to others.
Yeah. So that's why, because as you can see, the model has learned something, but it thinks that this could be 7 also. Now you see the beauty of ML model. Like you haven't taught it anything, but it itself learned something. Okay. Now let's see the another output. So as you can see, the probability of 2 is perfectly 1. It could be lesser than 1 also, but it should be very high. That's when you get a really good model. Okay. It thinks that this 2 could be near to 1 also, because sometimes you draw 1 like this. So that's why it's thinking that this could be 1 also, but other things it doesn't think. And it also thinks it could be 3 also. I think because if you just complete by doing adding one more small thing below it, it can become like 3.
Correct.
Okay. So here basically you are detaching it, getting it into CPU and getting in the NumPy. Basically you can see what should be the result. The result should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6. And as you can see, the results are matching. So this is also very important actually, that the thing that we went through the probability, you should also see like what it is thinking, what it is learning actually. This is very important part of ML model. Like before delivering the model, you should see, you shouldn't treat it completely black, like a black box. You should also treat it something like what it is internally thinking. So let's say now we got an idea like it somehow confuses between 2 or 3, let's say, assume in future. So at that time, we'll ask the people collect more data around 2 and 3. Once we have more data around 2 and 3, then we will retrain the model and ask it what is 2, what is 3. And I have listed something like other things people can follow, like what is the CNN and other things, and even TensorFlow. This was in Pytorch. Most of the people are going to Pytorch nowadays. Even Keras is fine if people want to do that. But I think this was the complete tutorial. Yeah.
Okay, cool.
Yeah. You have any other questions?
No, I think I'm good for now. Let me stop recording.
Yeah.